It is a great honor to be here for an academic exchange with you. The title of my report today is Single Value Decomposition of Split-Quaternion matrices and its applications for color image processing. The main purpose of this practical class is to help everyone understand the split-quaternion algebra, learn how to compute the single value decomposition of split-quaternion matrices, and explore its specific application schemes in color image processing. In addition, we will discuss the research directions and prospect of split-quaternion single value decomposition in color image processing. First, let's introduce the definition of the split-quaternion algebra. In 1843, William Roman Hamilton first introduced the concept of quaternions. After its work in 1849, James Cook proposed the split quaternions. It can be expressed as H being equal to the sum of H1, H2i, H3j, and H4k. I, j, and k are three imaginary parts. Let HS denote the set of split quaternions. HS is similar to the set of quaternions. It is also a non-commutative four-dimensional Clifford algebra. In the split quaternion algebra, adding or subtracting split quaternions involves combining their corresponding real and imaginary components directly. For multiplication, you describe each term of the first split quaternion across the second and apply specific rulers for the image units. The units behave uniquely. When squared I equals -1, where j and k equal 1. When multiplying different image units, the result is another unit, with the sign potentially changing depending on the order of multiplication. This means that the split quaternion multiplication does not satisfy the commutative ruler. In addition, since division is not defined in the split quaternion algebra, it is referred to as a ring rather than a field. Specifically, the split quaternion ring HS contains elements such as zero divisors, nilpotent elements, and non-trivial idempotents. It includes zero divisors, meaning that the product of two non-zero elements can equal 0, which adds to the complexity of its study. Regarding the application areas of the split quaternion algebra, scholars have recently discovered that it provides a unified framework for representing multidimensional data, aiding the efficient modeling and processing of complex spatial information. Its theoretical foundations and algorithms have recently been applied in various fields, including quantum mechanics, electromagnetics, signal processing, and color image processing. Given the increasing complexity of modern data and the demand for effective tools, further exploration of these mathematical structures is critical for advancing techniques in these areas. Here, I have listed some relevant references. Those interested can download and review them. This class primarily focuses on the application of split quaternions in the field of color image processing. We will briefly discuss how color images are stored and processed in computers and the split quaternion matrix model for color images. Space representations of color images in computers typically involve encoding the image using multiple color channels. Each pixel in a color image is represented by three primary color channels: red, green, and blue. RGB. The RGB repetition is the most intuitive and simple method for encoding color images. This simplicity allows for easy understanding and adjustment of color values, making it a popular choice in various applications. The intensity of each channel is stored as a numerical value, typically ranging from 0 to 255 for 8-bit images, which conveys the color information. The intuitive approach enables efficient processing and rendering of color images in computer image processing tasks. In addition to the RGB model, other color representations such as HSV, YCBCR, CIE, LAB, and CMYK are also used in specific applications, including feature extraction, video processing, visual perception, and painting. Here, I have also listed the MATLAB functions for converting between different space representations of color images, RGB to HSV, RGB to YCBCR, RGB to LAB, HSV to RGB, YCBCR to RGB, and LAB to RGB. They are built-in functions that can be called directly. However, there is no built-in function for converting between RGB and CMYK color space. I have only provided the conversion formulas, so those interested can try writing their programs to convert between this color space. Due to storing a color image in a computer as 3 real matrices and the strong spectral correlation among the RG and B channels, the color image model based on 4-dimensional algebra effectively preserves the internal connections between the channels. The split-coordinate matrix model enhances this overall channel relationship, helping to address complex color processing tasks, or rather than treating each channel separately. Based on this, a color image model using split-coordinate matrices has been established following the coordinate matrix approach. After establishing the split-coordinate matrix model for color images, we can further explore the diversity of applications based on SVD in color image processing. SVD is a powerful mathematical tool that demonstrates significant potential in various areas, such as dimensionality reduction, feature extraction, and image compression. Moreover, SVD-based methods offer more adaptable and robust solutions for handling complex image analysis tasks. By effectively extracting the mean feature of images, they assist in achieving more accurate color restoration, image reconstruction, and image classification. This further highlights the importance of conducting in-depth research on SVD, particularly within the framework of split-coordinate matrices. In the next section, we will explore the SVD of split-coordinate matrices and analyze their advantages and application concepts in color image processing. Here are some samples of split-coordinate matrices are shown here, such as transpose conjugate transpose, unitary matrix, Hermitian matrix, and so on. It is worth noting that the definition of I-conjugate transpose is special, and the modulus of the elements is also different from that of coordinates. One of the key focuses in the study of properties of high-dimensional algebraic matrices is their algebraic isomorphism. This repetition not only aids in a deeper understanding of the structural characteristics of split coordinates, but also establishes a clear correspondence between split coordinate matrices and their real matrices. Researchers can leverage well-established techniques from real analysis to address changes in the split coordinate algebra, ultimately leading to more efficient algorithms and solutions suitable for practical applications. Given any split coordinate matrix, a unique real matrix corresponds to it, known as the isomorphic real representation matrix of the split coordinate matrix, which satisfies equation 2.1. Conversely, for any given real matrix, a unique corresponding split coordinate matrix, this one-to-one correspondence ensures that the study of split coordinate matrices can leverage their isomorphic real representation, offering an efficient framework for analysis. In contrast, traditional coordinate matrices correspond to a structural matrix form that often involves increased computational complexity. From another perspective, split coordinates form a four-dimensional real vector space with the basis 1ijk. A mapping function denoted as phi associates this basis elements with a specific 2x2 real matrix. This mapping creates an algebraic isomorphism between split coordinates and real matrices, establishing a one-to-one correspondence between split coordinate matrices and real matrices. In other words, each split coordinate matrix can be expressed as a linear combination of four basis matrices in the real matrix space. Therefore, the single value decomposition of the split coordinate matrix can be obtained by the equivalent construction method. In the first step, for the SVD of a real matrix, we can easily obtain equation 2.4, where U and V are two unitary matrices, and D is a diagonal matrix containing non-zero single values arranged in descending order. In the second step, we use the single values of the isomorphic real matrix to reconstruct the single values of the split coordinate matrix. From the isomorphic real representation of split coordinate, we know that each corresponds 1-to-1 with a 2x2 real matrix and vice versa. Following this principle, we can pair adjacent diagonal elements in matrix D to form a diagonal matrix corresponding to a split coordinate. As shown in equation 2.5, each of these paired elements uniquely identifies a split coordinate, representing a single value of the original split coordinate matrix. By continuing this process, we can find all single values of the original split coordinate matrix by pairing the diagonal elements of D in sequence. Similarly, for the left and right single vectors of a split coordinate matrix, we pair the left and the right single vectors of its isomorphic real matrix by combining order and even index vectors to obtain the unique corresponding split coordinate vectors. Notably, if single values are paired by grouping the first and the second values for the isomorphic mapping, then the single vectors are paired by combining the first and the second columns. In this way, we can identify all left and right single vectors of the split-quaternion matrix as shown in equation 2.6. Thus, by integrating the reverse construction process discussed, we can obtain the SVD of the original split-quaternion matrix from the SVD of its isomorphic real matrix. Additionally, two important points should be noted regarding the SVD of split-quaternion matrices. First, their single values are no longer traditional real numbers but take a new form, A plus BK, while still being ordered by their modulars in descending order. Second, the matrix VH describes the I conjugate transpose of the matrix rather than the conventional conjugate transpose. Here we present the MATLAB code for computing the SVD of a split-quaternion matrix. Since split-quaternion matrices are not recognized in computers, the input for the function consists of the coefficient matrices A1, A2, A3, A4 corresponding to the basis of the split-quaternion matrix. The output includes the coefficient matrices for the corresponding single value decomposition U1, U2, U3, U4, S1, S4, and V1, V2, V3, V4. Next, compute the real representation matrix of the split-quaternion matrix A. Get the size of A. Perform SVD of phi A. For computing the SVD of real matrices, MATLAB provides built-in functions that facilitate the process. Extract the diagonal elements of DS. Next, based on the formulas, we can construct the U, S, and V matrices for the SVD of the split-quaternion matrix. Since split-quaternion matrices are not necessarily square, it is important to supplement the right or bottom side of the diagonal matrix with zero matrices, depending on the dimensions of the original matrix. If you are interested, you can also replicate the computation process for the SVD of a split-quaternion matrix. Now that we have computed the SVD of the split-quaternion matrix, what advantage does it offer for image processing? We can conduct a brief analysis of its benefits from the perspectives of computational time and the feature preservation. Let's examine the first experiment. In MATLAB, we simulated color image data with varying pixel size ranging from 20 to 800 with pixel values between 0 and 255. The round function is built in a rounding function, where rand creates random numbers between 0 and 1. We constructed both traditional quaternion matrix models and split-quaternion matrix models from the simulated pixel matrices and performed SVD on them. On the right side, we present a graph showing the computation time. The x-axis represents the size of the pixel matrices, and the y-axis indicates the time taken for computation. We compared Our SVD algorithm for split-quaternion matrices with traditional quaternion SVD computation algorithms, including the quaternion toolbox, the real structure preserving algorithm processed in 2014, and the complex structure preserving algorithm introduced last year. Our approach demonstrates a significant advantage in decomposing color images. The second set of experiments focus on the feature preservation of SVD. We used randomly left-sided color images to construct traditional RGB models, quaternion matrix models, and split quaternion matrix models performing SVD on each. We selected some largest singular values and their corresponding singular vectors for image reconstruction. To analyze the relative error, we compared the reconstructed images with the original images broken down by RGB components. It is important to note that both the quaternion and the split quaternion matrix models produce real components, which we omitted since only the imaginary components coefficient matrices are needed to represent the reconstructed color image. On the right, we present the error graph, where the x-axis represents the number of selected singular values and the y-axis shows the reconstruction error. This graph compares the reconstruction errors of the traditional RGB model and the quaternion SVD. Our algorithm demonstrates a significant advantage in preserving features in color images. From the two experiments, it is evident that the SVD of split quaternion matrices offers distinct advantages in both computation time and feature preservation. This method serves as an excellent tool for large-scale image recognition, feature reselection, sparse optimization, and other aspects of color image processing. Next, we will provide a detailed description of the image processing algorithms. The focus will be on extending the advantages of the SVD of split quaternion matrices to existing image processing frameworks to address practical implementation changes. Additionally, we aim to establish new efficient image processing solutions to facilitate the presentation of image processing algorithm performance. We first introduce several visual fidelity metrics. The first is the widely used peak signal to noise ratio (PSNR), standard metric for assessing image reconstruction quality. Higher PSNR values indicate that the reconstructed image is closer to the original. In MATLAB, a built-in function is available to calculate the PSNR between the original image H and the processed image hot H. The second is the structural similarity index, which evaluates the similarity between two images in terms of luminance, contrast, and the structure, aligning more closely with human visual perception. SSRM value closer to 1 indicates better algorithm performance. MATLAB also provides a built-in function for directly calculating SSRM between images. The third is normalized correlation, NC, which measures the similarity between two images by normalizing the cross correlation. This metric is useful for typically matching and assessing alignment, which values closer to 1, indicating better algorithm performance. It is commonly used in evaluating watermarking algorithms. MATLAB does not provide a built-in function for NC, but interested users can define a function based on the formula provided here. Next, we introduce color image processing algorithms, starting with the decomposition and restoration of color images, which can also be referred to as color image compression and restoration. Mathematical addition: in this formula, a color image A is represented using the color channels R, J, and B combined with bases I, J, and K, respectively. The image is then decomposed into a sum of rank 1 matrices, each constructed from column vectors mu1, mu2, mu-r of matrix U, and column vectors nu1, nu2, nu-r of matrix V, scaled by the corresponding non-zero diagonal elements sigma 1, sigma 2, sigma of matrix sigma. In image compression, it is essential to introduce the compression ratio as a control metric. The compression ratio CR is defined as the ratio of the data capacity of the original image to that of the compressed image. Specifically for an M by N image, the compression ratio can be calculated using the formula 4.2, where T represents the number of selected single values or single vectors. Next, we present a specific image compression program in MATLAB. This approach is similar to image single value decomposition, but differs in that it uses the compression ratio to control the amount of data to be stored. For example, if we aim to compress the original image data to a compression of CR, we need to determine the amount of data to be preserved. The original color image consists of 3 M by N real matrices. After decomposition, we assume that matrix U returns the first T columns. The matrix V also returns the first T columns, and the single value matrix keeps the first T diagonal elements. Consequently, we can easily calculate the appropriate integral value for it using equation 4.2. For image reconstruction, we only need to approximate the original image by combining the rank 1 components after color image decomposition. Once the combination is complete, it's necessary to convert the data from double precision to single precision. The function I'm sure is then used to display the reconstructed image. Table 2 represents the compression ratio formulas for several commonly used SVD-based color image decomposition and reconstruction methods, including SVD, split-quaternion, SVD, commutative quaternion SVD, 3 types of quaternion SVD algorithms, and SVD of the RGB 3 channels. Additionally, and the same compression ratio and data storage capacity, we also display the reconstruct color images and their corresponding PSR values. Clearly, under the same experimental conditions, the SVD of split quaternion matrices demonstrates superior data compression and reconstruction advantages. The second algorithm to introduce is designed for embedding and extracting color watermarks. This algorithm embeds watermark information within the feature space of color images to ensure transparency and robustness. During the embedding phase, specific key features of the image are used to integrate the watermark in a desired form. The extraction phase then reverses these operations to recover the watermark from the clear image, ensuring accurate extraction even in the presence of interference. This algorithm primarily applies to copyright protection, content authentication, and anti-counterfeiting. The watermark embedding process involves several key steps. First, we pre-propose the color host image by separating it into RGB channels and then constructing a pure imaginary split quaternion matrix. Next, we pre-process the color watermark image by dividing it into RG and B components, ensuring that the host image dimensions are integer multiples of the watermark dimensions. To enhance the watermark's security, we apply an node transformation to each component, forming a corresponding pure imaginary split quaternion matrix. Following the pre-processing, we divided the split quaternion matrix of the host image into non-overlapping patches and perform SVD-SQ on each page. We then extract the maximum single values from all pages to form a matrix, which is linearly combined with the watermark at a specified strength. This combined matrix is then decomposed again via SVD-SQ to embed the watermark. Finally, we recombine the watermarked patches to obtain the final watermarked image. This structured approach ensures the transparency of the watermark while enhancing its robustness against interference and attack. The following MATLAB program investigates the watermark embedding process, incorporating specific details for each step. First, the host image is converted from single to double precision, and its RGB channels are separated. Next, the watermark undergoes node scribbling to enhance its security. The host image is then divided into blocks, and SVD is performed on these blocks. From this, the maximum single values are extracted to form a new single value matrix, which is also subjected to SVD. The watermark is embedded by executing a linear combination with this single value matrix. Finally, the content on page 36 outlines the reconstruction of the watermark date back into the host image, completing the watermark embedding process. The watermark extraction process begins with preprocessing the watermark image by separating it into RGB channels, which allows for the reconstruction of corresponding pure imaginary split coordinate matrix. This matrix represents the color information in a structured manner. Next, the split coordinate matrix is divided into non-overlapping patches, simplifying the extraction process by breaking the date into manageable segments using a predefined watermark extraction key. The watermark information is then extracted from each page through the application of the inverse single value decomposition technique. This critical step enables the accurate retrieval of the embedded watermark. Finally, the extracted watermark information is reconstructed to ensure its completeness and integrity, demonstrating the effectiveness of this method in watermarking applications. The MATLAB program for the watermark extraction process closely follows the watermark embedding procedure. With a few key adjustments, it begins with processing the watermarked image by separating it into RGB channels and converting it into a pure imaginary split coordinate matrix. Afterward, the watermarked image and ghost block SVD dividing it into patches to simplify extraction. The next step involves reversing the linear combination used drawing embedding to retrieve the scribbled watermark date. Finally, the inverse scribbling operation is applied to recover the original watermark, ensuring its integrity and usability. This approach effectively demonstrates the use of split coordinate matrix and SVD techniques in watermark extraction. Next, we will present a detailed analysis of the experimental results. First, let's discuss the experimental setup. Figure 5 shows all the color host image used in the experiments, which were sourced from the CVG UJR and Kodak databases, with each image resized to resolution of 512 by 512 pixels. Figure 6 shows all the color watermark images with different pixel resolutions used in the experiments. Next, we present the watermarking schemes tested in the experiments. All the listed schemes are based on matrix decomposition, with scheme 10 being our watermarking approach. Currently under second review. If published, interested readers can refer to the corresponding article for further details. The analysis of the specific watermark experimental results includes the following sections. First, analysis of watermark embedding payload. Watermark payload refers to the capacity or moment of watermark information embedded in an image or another digital media used to evaluate the embedding capacity of a watermarking algorithm. In Table 3, larger values indicate a rich embedding payload of the watermark. Taking scheme 1 as an example of the binarization watermarking scheme, a host image with the resolution of 512 pixels can accommodate maximum watermark size of 45 pixels, resulting in the maximum embedding rate is approximately 0.0618. In practical experiments, however, a watermark size of 32 pixels is typically used. According and actual embedding rate is approximately 0.0312. Taking scheme 6 as an example, a host image with a resolution of 512 pixels can accommodate a maximum watermark size of 128 pixels, resulting in the maximum embedding rate is approximately 0.0625. In addition, since our watermark scheme only requires that the watermark size does not exceed the size of the host image, the maximum embedding rate is 1. Second, analysis of computational complexity. The computational complexity of matrix decomposition refers to the resources required to perform decomposition in watermarking schemes used to size the scheme's efficiency. In Table 4, larger values indicate a higher computational complexity, as shown in Table 4. Sure decomposition and SVD based on RGB channels have relatively lower computation complexity. Following this are SVD based on split-quaternion matrices, where pure decomposition and SVD based on quaternion matrices have higher computational complexity. This computational complexity only reflect watermark embedding efficiency from a mathematical perspective. Different extraction methods will also impact the efficiency of watermark processing. Third, analysis of computational runtime refers to examine the time required to execute a watermarking algorithm, which helps assess its efficiency and suitability for practical applications. Table 5 presents the average time for embedding and extracting each watermarking scheme based on multiple trials. The color digits indicate the maximum runtime. In Table 5, our runtimes of less than 1 second and marked with color numbers. It can be seen that the runtime of the SVD-SQ based color watermarking scheme is nearly the same as that of the RGB 3-channel watermarking schemes, indicating that the watermarking scheme using this four-dimensional algebraic structure does not significantly increase in the runtime. However, the other Courtney watermarking algorithms have significantly longer runtimes. In addition, as Scheme 9 does not need to perform Courtney SVD again during the instruction process, the instruction time is faster, but the overall time is still slightly slower. Fourth, invisibility analysis refers to evaluating how well the embedded watermark remains visually or audibly undetectable within the host media, ensuring that the watermark does not compromise the quality or appearance of the original content. Table 6 presents the average results of the experiments involving the provides a combination of the original host images from Figure 5 and the watermark images from Figure 6 using the quantization values recommended in the original literature for embedding and instruction. It shows the average PSNR, SSIM, and NC for each scheme. The PSNR of the watermarked image is 30, and the closer the SMIM value is to 1, the less interference there is with the host image, indicating better quality with higher PSNR values. Additionally, NC value closer to 1 indicates better watermark instruction performance. Next, robustness element analysis refers to the assessment of how well the embedded watermark can withstand various attacks or alterings, such as compression, cropping, or noise, ensuring that it remains detectable and intact under adverse conditions. In Figure 7, search and papers noise of 0.05 times intensity was added to the watermarked image, and then the watermark was extracted. Testing the watermarking scheme under different attack conditions is essential for understanding its effectiveness in practical applications. The experimental attacks, including noise, addition, rotation, brightness adjustment, contrast adjustment, filtering, JPEG compression, and combination attacks to compare the robustness of the color watermarking scheme as fully as possible. Table shows the extraction results using the same host image and the watermark image. The quantization parameters of each watermarking scheme are carefully selected to ensure that the PSNR of the watermarked image is greater than or equal to 35 as far as possible. The experimental design includes no attack test on the image after embedding the watermark, as well as the 13 attack tests. Scheme 10 demonstrates superior experimental performance. Next, color image fusion single value using single value decomposition is a technique that combines multiple color images of the same sign into a single composite image, effectively preserving the most significant features from each source. SVD is practically useful in this context because it decomposes images into their constituent components, allowing for the identification and retention of important features while discarding less relevant information. This process not only enhances image quality but also improves object recognition and increase both spatial and spectral resolution. Due to time constraints, only some relevant concepts and literature will be introduced here. Those interested in this area are encouraged to pursue further research. Similarly, for color image denoising and recognition based on SVD methods, most existing techniques are based on coordinate matrix SVD approaches. However, the application of the split coordinate SVD in this content is still explored. This method harnesses the advantage of coordinate algebra to effectively process color image data, leading to improved denoising and recognition performance. In conclusion, we summarize the key points discussed in this course regarding the advantages and the disadvantages and future research directions of SVD based on split coordinate matrices. The advantages of SVD SQ based color image processing include the complex representation of multidimensional information, which ensures full portrayal of both color and spatial data. Additionally, this method features low complexity and high speed, significantly reducing the computational load and enabling fast processing. Furthermore, it provides strong feature retention, preserving essential structures and color fidelity, resulting in high quality outcomes. These benefits make SVD-SQ an effective approach for various applications in color image processing. The disadvantages of SVD-SQ based color image processing include real part redundancy, where the computation process creates redundant real components that can negatively impact the overall efficiency and increase storage requirements. Additionally, split coordinates introduced non-equivalent component representation, which differs from traditional coordinates. This can lead to increased complexity in the processing framework and may affect the interpretability of the results. Next, here we also we use two images to illustrate the non-equivalent component representation of the split coordinate matrix model. Specifically, we select three different components of the split coordinate matrix to represent color images and demonstrate the suitable difference in reconstruction quality. The results inhibit certain regardless when the real part of the I component of the split coordinate matrix is set to 0, the reconstruction results are identical. Similarly, enhancing the changing the J and K components yields the same outcome. Moreover, regardless of the exchange, the reconstruction quality of the split coordinate matrix model consistently outperforms that of the coordinate matrix model to a certain extent. Next, building on the aforementioned advantages and disadvantages, the next phase of research can focus on several key areas. First can be made to optimize real part redundancy to enhance computational efficiency. Additionally, developing adaptive strategies for managing non-equivalent component representations will be critical for improving the processing framework's effectiveness, establishing equivalence replacements from SVD-Q to SVD-SQ in color image processing will also be important consideration. Finally, there is potential for developing new color image processing schemes based on SVD-SQ, which could lead to innovative applications and improvements in this field. These directions will help advance the understanding and practical use of SVD-SQ in color image processing. This concludes the course content. Thank you for your attention.